Okay, well, hi everyone. Today I'm going to talk about how to boost the quantum communication and to achieve a channel capacity with the GKP code. And also, our second half of the talk, I'll talk about like code-designed protocols that using quantum error correction for quantum transduction. So the motivation is actually like in the future, we hope we will have a global scale quantum network. And in order to achieve that, we need kind of like not only have like a kind of error corrections and correct like errors associated with a lossy bosonic channel, but we also need like some error correcting codes that hopefully will help us to boost the performance of quantum transduction between like say microwave and optical modes. Okay, so now that so in terms of like kind of achieving a quantum channel capacity, it will be good to actually look into like what we can do with our classical communication. So in the late 40s, Shannon came up with classical channel capacity, and it took more than half a century for people to come up with these LDPC code and the polar code, which is now widely used in our 5G network. And also for the bosonic case, for this continuous variable coding, we also use the phase-shifted keying and quadrature amplitude modulation for our Wi-Fi and Bluetooth. Okay, so now in the quantum domain, we also have some understanding about the quantum channel capacity, but there are still open questions about the super additive channels, which still don't know exactly what the capacities are. However, for particular channels like a pure loss bosonic channel, like what is sending information over fiber, we actually know exactly what the channel capacity is. So the task is actually to come up with really good, efficient codes, like a QLDPC code or even quantum polar code, to achieve some of the capacities. And also, like for bosonic case, which is the focus of today's talk, is that I would propose actually we can also investigate the GKP code, which is a promising code that will show that you can achieve quantum channel capacity. So just as give you some intuition, in our classical codes that for our Wi-Fi and Bluetooth, we actually can send like a weight packets of bosonic mode. And the information can be encoded in, if you think it as a harmonic oscillator, there is a position and a momentum quadrature. And you can come up with these lattice of these different coherent states or different thermal states. And as long as they're distinguishable, you can use them to store information. So if you have these lattice of 16 coherent states, then you can store 4 classical bits of information. And in the quantum case, you can come up with some similar designs. And the choice of the quantum code, you can say, define a 2-dimensional subspace. And the projection of that 2-dimensional space can give you a 2-dimensional, like a logical qubit. And the GKP code, it actually has a similar lattice pattern. Unlike a classical case, you can measure position and momentum. In the quantum case, we know we cannot simultaneously measure position and momentum. But what we can do is we actually can measure position and momentum modulo some constant. And if these lattice spacing satisfy some symplectic form, then we actually will be able to measure the deviations from these lattice modulo those constants. So that is actually the essence of the GKP code. So I guess for this audience, probably people are familiar with the stabilizer formalism. So let me define the GKP code in terms of that. So we know that the position and the momentum, they don't commute. The commutator is a constant. That means that if we perform this using BCH formula, we can do like a closed loop 4-step displacement that encloses area. And that area, if it's integer multiple of 2 pi, then we know that these 4 operations, the product will be proportional to identity. And that means we can come up with these 2 stabilizers. One corresponds to displace along the momentum direction by 2 times root 2 pi, and the other corresponds to displace along the position direction by 2 root 2 pi. Then these will commute with each other. And if they commute, we can define the co-eigenstates with eigenvalue +1, and that will define our logical space. And here I intentionally choose the area enclosed to be 2 times 2 pi, so that there will actually be a 2-dimensional logical space encoded. And the way to see it is actually to take a square root of the stabilizers, similar to what we do with the surface code. Then we'll find that actually we can have a displacement which, instead of 2 root 2 pi, the displacement is a square root of pi along position and momentum directions. And you'll find that these logical operators commute with the stabilizer, while the logical operators, they anti-commute with each other. which form a logical poly and a logical Z. Okay, so that says there is at least a two-dimensional logical space in the system. And the argument is very similar to Tauri code, but here it works for the continuous variable system. All right, so now to visualize the GKP code, you can actually plot the logical 0, logical 1, or logical plus, logical minus. And here, in order to have a well-defined code, we actually put a Gaussian envelope. But if we don't constrain photon number, then we will see the exact translation invariant symmetry, which is associated with the stabilizer. For example, the Sx corresponds to translate along the position direction by 2 root pi, which you will see that actually you do have this periodicity of 2 times root pi when you translate along the position direction. Similarly, when you translate along the momentum direction, you also see these periodicities for both these code words, for all these code words. Moreover, you can actually consider the logical operator, which corresponds to, say, logical x, is a translation along the position direction by root pi, which you see when you translate half of that periodicity, you actually go from logical 0 to logical 1. So that shows that actually, indeed, you can apply a x logical, which is a translation by root pi along position direction. You go from 0 to 1 in the logical basis. Okay, similarly, you can do that translation for momentum. Okay, so later we'll actually use some of these properties actually to argue that that we can design new codes for transduction schemes. But here is just the property. You can think that the 0 corresponds to the position in some even lattice sites, whereas the 1 state corresponds to the position basis in odd lattice sites. Okay, so having these discretized lattice sites in the harmonic oscillator's position and momentum, it allows us to correct small displacement errors. Because the code words should be in the integer lattice sites, but if there's a deviation with small displacement error, we actually can physically measure the real and the imaginary part of these stabilizer operators, and from which we can infer what is the nearest lattice point, or what's the deviation from the lattice point, and correct those errors. Okay, and there are various ways to correct these errors, but here at least you can, in principle, measure these stabilizer. And moreover, here for simplicity, I show the square lattice GKP. You can also come up with other symplectic lattices like a hexagonal lattice, which can give you more efficient packing with potentially better performance. Okay, so now, so far I'm thinking about correcting displacement error, but in reality, what we really care is actually the excitation loss error, such as communication that you go through a lossy channel. So this is a way to convince yourself that actually, if there's an error correcting code can correct the random displacement, small displacement error, it actually can also correct loss error. The way you can think is the following. Suppose you have a coherent state. In the presence of pure loss, the amplitude of a coherent state decreases. And then you can do a phasing sensitive amplification to restore the original amplitude of a coherent state, while at the same time amplify the intrinsic vacuum noise a little bit. And that works for single coherent state. It also works for superposition of coherent states, which can span the entire Hilbert space. So therefore, for any states, you can think that the loss followed by amplification gives you a random displacement. Therefore, any error correcting code can correct such a random displacement error. It should also be able to correct a pure loss error, simply by amplify it and do error correction. So therefore, it's kind of, in retrospect, not too surprising that GKP code can correct pure loss errors. Okay, and experimentally, people have make significant advances in bosonic error correction from CAD code, binomial code, and recently from Michel Devrio's group, demonstrate you can do the GKP code for logical qubit or logical qubit with 3 level and 4 level, which you can boost the coherence time by a factor of 2 or more. So now, one natural question is GKP code the optimum choice of the code? Right? What's the fundamental limit of these bosonic error correcting codes? So in order to understand that, we're going to first numerically show that actually GKP code emerges as a good choice of the code, and then analytically give a justification, and also prove that it achieved channel capacity performance. So one way to model the error correction is simply encoding and decoding. So you have say a logical qubit you want to encode into some bosonic modes, And after interacting with a noisy environment, you want to decode it and restore the original logical qubits. And here there's always ambiguity whether we should put in logical 0, logical 1, or logical plus or minus. The way to avoid ambiguity is to put a maximum entangled state with some reference system. And that avoids ambiguity because in the end, you just measure whether you still restore the original maximum entangled states. And you can define entanglement fidelity as the overlap of the final output states going through all these encoding, noisy channel, and recovery. What's the overlap with the ideal maximum entangled state? And that's called entanglement or process fidelity. And the reason we choose such a fidelity is because it's a linear function of encoding or the noise or the decoding, which means that we can actually do some like semi-definite programming to optimize these different operations. And because we're doing numerically, we also need to put some upper bounds about the average code number, average photon number for the code. So what one can do is the following. Let's fix the encoding, and we can actually use semi-definite program to optimize the recovery. And then we can fix the recovery and optimize the encoding. And we can alternate the optimization between encoding and the recovery. And what happened is that initially you can choose arbitrary, kind of like a two-dimensional projections. And after these few iterations, a few hundred iterations, you will see that the hexagonal lattice appear. And that exactly corresponds to the projection of the hexagonal lattice GKP code. So it doesn't matter what the initial kind of like a two-dimensional code space you choose from. After this optimization, it turns out that the hexagonal lattice GKP emerges as the optimum encoding. And here we actually consider 10% loss. And if we choose this if we relax this to like 10 photons, you'll find that actually we can correct 10% loss error and restore the fidelity with 99.99. So basically, it shows that with additional levels of the bosonic system, you can significantly efficiently suppress these loss errors. And then there are two questions emerge. Why hexagonal lattice is optimum? We know it's efficient packing, but what's the connection with packing and error correction? The other question is, well, what exactly is the optimum GKP we can do? Here we push it to average to be 10 photon. What about average to be 100 photon or more? And when doing this calculation, actually, when Victor Albert was doing that, he actually burned his classical computer memory. So basically, this is something shows that, okay, there's some limitation we can do numerically, so we need to come up with some more efficient analytical approaches. So in order to understand that, actually we need some develop some formalism. What we need is actually, instead of numerically using semi-definite program to find the optimum solution, we actually hopefully will have some analytical way to write down some near optimum solution. And the way to do it is something we call the transpose channel. So here's the definition of a transpose channel. Okay, suppose we have a noise channel which consists of a mixture of different cross operators. Then the transpose channel is basically try to invert the cross operator. So basically, instead of the n, you actually write an n dagger for your this transpose channel operation. But in order for this channel to be complete positive trace preserving, you need to do some normalization and also projection. So for a simple case, if this noisy channel is a unitary channel, then the n dagger undo that unitary. And the other parts just takes care of the normalization. And there is actually one nice feature about this transpose channel is it's actually sort of guaranteed it will be close to optimum because the infidelity of this recovery is within a factor of 2 away from the optimum recovery. So basically, if we don't care about that factor of 2 of the infidelity, we basically can say this is close to optimum. Okay, and the good thing is everything you can write down analytically, and you can do the calculation, and in the end can compute what is the fidelity of the logical encoding followed by this near optimal recovery with transposed recovery. And it's just a function of error correction metrics. Because once you fix your encoding, you can exactly know, and the noise channel, you know exactly what the error correction matrix is. And therefore, this is just the function of error correction matrix. So that allows us to compute more complicated situations. So now for pure loss channel, if we assume the average encoding photon number being very large, approach infinity, we actually can get for square lattice GKP, this is simply a function of the loss of the bosonic channel. So this function is actually very interesting because it has the exponentiation of minus a constant times 1 minus gamma over gamma. So gamma is the loss rate. So when the loss rate is very low, this will become e to the minus infinity, which means that the error or the logical infidelity will quickly vanishes as the gamma become very small. And also this function is analytically discontinuous when gamma approaches 0 because it just quickly goes to infinity. For example, when you kind of have 10% loss, here we show that actually this asymptotically, instead of 10 to minus 4 with 10 photons, you actually can approach 10 to minus 6 if you have hundreds or more photons. Moreover, if you reduce this loss by a factor of 2, you actually squared the effective error at the logical level. So you can push to 10 to minus 12 or even better if you only have 5% loss. So this is actually shows a really good potential of the quantum error correction. But of course, here I want to point out this prefactor is very important. It's pi over 2 because we're using the near optimum recovery. If we just use the simple-minded amplification and the GKP recovery, the prefactor in the exponent is pi over 8. So there's a factor of 4 difference in the exponent. So if we just say 10% loss with the simple-minded amplification and GKP recovery, we only get an infidelity of 3%, while if we do the optimum one, we get 10 to the minus 6. So this is a huge difference, which shows it's important to do this near optimum recovery in order to get the most from these bosonic codes. And of course, here we still say mathematically we can write down the near optimum recovery, and it's still an important research question to see how we can robustly implement such a recovery. But here it just shows that fundamentally what is the capability of these bosonic codes. So now we can go from the square lattice codes, which the prefactor is pi over 2. Can we do better with more efficient packing? And here the answer is yes. If we do hexagonal lattice, it actually can be better. So here we can also do the D-level coding. So instead of pi over 2, we can do pi over D if we do D-level coding with square lattice. And if we do hexagonal, it's 2 over root 3 pi over D. That's associated with the efficient packing, associated with the hexagonal. And we can generalize to any symplectic lattice. It's some prefactor multiplied by kind of this is actually associated with the dual, symplectic dual of the original lattice. And the error is associated with, is limited by the nearest lattice point of the symplectic dual. So what happens is that if you have efficient packing of your physical, of your phase space lattice, then the symplectic dual, if it's initially a physical space, phase space is efficient packing, then the dual space will actually give you larger spacing. So the larger spacing means this quantity is large, so therefore the effective logical error will be smaller. So that's actually the reason why we need the efficient packing in physical space, so that you'll have larger spacing in the dual space, therefore the effective error will be smaller. So here's just the illustration of the red dots being square lattice, and these blue triangles just show the hexagonal lattice, which is a little bit larger in the dual space. So therefore, it actually gives better suppression. So that shows, that kind of give you a theoretical explanation why efficient packing is important and related to error correction. Now, this is just for a single mode bosonic codes. We can also extend the formalism to think about the higher dimensional symplectic lattice. And we can also get analytic formula and to bound the performance of multi-mode GKP code. And this time, the goal is actually to achieve the channel capacity. So here is actually we can bound the infidelity using a similar formula in terms of the efficient packing and the dual lattice in the symplectic dual lattice, and then we can bound the error. So it basically becomes a sum over this expression associated with the non-trivial lattice point in the symplectic dual lattice. And we actually can use this the theorem from Burns and Steinach, say there exists a symplectic lattice that they can upper bound this sum over lattice point by an integral. And because this expression is quadratic, it becomes a Gaussian integral, so we can compute the upper bound for that. And you'll find the upper bound is just a constant multiplied some number to the power n. When n go to infinity, this will vanish if this product inside the exponentiation is less than 1, which means we can just choose this quantity, which corresponds to the number of levels encoded in each bosonic mode, is upper bounded by the function of a loss rate. Then we will have a vanishing infidelity of the coding. And this number, when you take a log, it just corresponds to the code rate. So therefore, we obtain the code rate that is actually asymptotically approach the channel capacity of pure bosonic loss channel. And here you'll find that suppose if gamma is, say, 10% loss, this number is about 9, and we take a log base 2, it says that actually with 10% loss, you can roughly encode 3 logical qubits per bosonic mode. And earlier we only did 2, which is, but actually you can actually do like a lot more. Yeah. So that basically shows that earlier we only know like there is a bound which have a similar scaling, but now we can actually close the gap and claim we can achieve this channel capacity. And there's also another technical detail which we overcome recently, because when we close the gap, it only works for some special points of loss, and we can overcome those special points of loss by combining a single mode GKP code with a quantum polar code, so that effectively at the logical level, you can achieve this channel capacity for any loss rate. Yeah, but those are maybe a bit more detail, and I would encourage people to look at these 2 archive papers for the detailed proof for the channel capacity achieving codes. Yeah, so for the remaining time, actually I want to kind of talk about another related topic, also about kind of like you will see GKP appeared again, but this time is actually about quantum transduction. So we know that, okay, we have, for example, superconducting platforms. We can do lots of computation over it, and if you want to connect a different superconducting quantum computer, we actually, like, if they're remote, it will be better we do the transduction or conversion from microwave to optical, send over optical channel, and then back to microwave to connect a different superconducting quantum computer. So basically, we need a gadget that can convert between different, like, microwave and optical signals. And this is like called a quantum transducer. And you can think that, okay, with additional like external pump, this transducer can be modeled as just like a beam splitter between microwave and optical modes. Okay, and now there is a difference like for transducer and our like a fiber channel. For transducers, you can actually control the input of both input ports, even if you just want to convert from A1 to A3. You can put something non-trivial in A2 that might potentially help you to boost the performance of the transducer. Okay, so now with that, let's first, okay, I assume like people are probably familiar with the beam splitter. And here I'm just trying to write down the Heisenberg picture in terms of the beam splitter, where you have A1, A2 mode coming in. The output mode is A1 prime and A2 prime. And the goal is actually try to transfer information from A1 to A1 prime. Okay, and we know that usually for simplicity, we often, well, most of the investigation we assume that A2 is vacuum. Then we just get a simple quantum loss channel, and with the efficiency eta, and this is the channel capacity. And here eta is 1 minus gamma in the first half of the talk. So from this expression, we see that when eta equal to 0.5, this become log to 1 becomes 0. So we need at least 50% transmission in order to be able to transmit quantum information through such a beam splitter. Okay, which is kind of consistent because it kind of also, you can also interpret as a no cloning theorem, right? Because here, probably environment shouldn't get more than what the receiver get in order to have such a finite quantum capacity. Now, one question is vacuum environment the optimum? Is it always good to just put the vacuum, or we should put something else? And one story we learned from gravitational wave detection is actually vacuum might not be optimum. We can put squeezed vacuum in here, and for LIGO, it actually can boost the performance. And here, actually, we also tried the squeezed vacuum. It doesn't help. But we also have other resources, like non-Gaussian states. That could also improve the performance. Okay, so now can we do something better by engineering the initial input state of the A2? Okay, and this is a setting which is different from just a pure bosonic loss channel. here we actually have access to this additional ancillary inputs, which is important and also practically relevant for transduction. So now here, we want to kind of like model the system as the following. We have A1, A2, and output is A1 prime. We have encoding from A1, and we have ancillary inputs, we call it the sigma from A2. And then the total channel is actually a channel that depends on the beam splitter transmission eta, as well as the ancillary input sigma. And that gives the channel acting on the input. Notice we actually, in some sense, we cheated because by putting some non-vacuum states, we actually modify the quantum channel. On the other hand, the state we put in here is a fixed state. It doesn't depend on what the logical information is encoded from A1. So this is a quantum channel, but for the channel, we actually need to consider what are the options we have. And actually, in the earlier studies, around a few years ago, people do find that if you put Fock states here, and they compute the coherent quantum information, they do find that actually, as you like increase the Fock state number here, you actually can get like non-trivial coherent quantum information for the system. Which means, in principle, you can send the quantum information through if you just put non-Gaussian states like Fock states through this ancilla. Now, the thing is, this value is not very big. It's just say like, okay, you probably can send like a 0.13 qubits per use of the channel, but it's a lower bound. And also the Fock states may not necessarily be the best choice. Okay, so now in order to understand, like, can we optimize it? We actually, again, look into numerical, optimization. This time, instead of just optimizing the encoding and decoding, we can also optimize the choice of the ancillary state. It doesn't have to be vacuum, it can be any state. So just similar to our optimization of the bosonic code, we can first define the entanglement fidelity, which is the linear function of encoding, decoding, and also the noise channel. And put the photonomial constraint. We optimize the recovery, optimize the encoding, and optimize the noise input this time. So we call this tri-convex optimization, and we iterate. And first, there's no guarantee that this will converge, but it turns out that it actually somehow miraculously does. And what happened is that we get the optimum input, which is hexagonal GKP again. Now, what's the optimized environment? It sort of looks like a hexagonal GKP state. It's a fixed state. You see negativities of the Wigner functions. Okay, and this is just say like even if we have 20% transmission with the average and 8-photon encoding, you can send a quantum state through with a better than 99% fidelity, which means you can actually transmit the information really, really reliably over this channel, even though there's only 20% transmission. So how can we understand what's going on in here? Because something must be like a miracle happening, and also we should have some explanation why GKP also worked in this case. Okay, so now in order to understand this, let's just recall what we do with the GKP code in terms of the square lattice GKP. One thing you need to remember is the logical 0 and 1 correspond to even and odd lattices, and the logical plus in terms of position, and the logical plus and minus becomes even and odd lattices in terms of the momentum. Okay, now we can consider like the beam splitter, and for simplicity, let's assume that the beam splitter only consists of like real elements that only mix between the position and the position, or the momentum and the momentum. And in this way, we can write the output position. It's just a linear combination of the position 1 and the position 2. And there's no mixing of the momentum. So the output, the position for A4 is also the linear combination of position 1, position 2. So therefore, what the beam splitter does is just a rotation from the initial like input position Q1, Q2 to the output position Q3, Q4. And that rotation angle depending on the beam splitter transmission. So if you have a perfect beam splitter, a beam splitter with a perfect transmission, then cosine angle is 0, which means that basically there's no rotation at all, you just go through. And if there's some like finite eta, then this rotation angle will actually be some finite angle. Therefore, you may not necessarily have all the information from Q1 being transferred to Q3. Okay, but the rotation is actually like pretty easy to visualize. Now suppose I have my initial information in A1 is as a GKP code. And recall that earlier I mentioned that the GKP code you have in partition even and odd lattices. And here I can label the Q1 with even and odd correspond to the even correspond to blue dots, and odd correspond to orange dots. And the Q2 is just some GKP codes, which there's no even and odd, it's just some lattices. So here I'm just showing that this is a lattice, not to be confused with phase space. This is just a coordinate of the position 1 and the position 2. Because position 1 have even and odd lattices with the blue and the orange, and the position 2 do not encode any information, it's just a regular GKP state with the square root of 2 spacing. So this is just like what's the input for A1 and A2 in their position. Now, after that rotation of the beam splitter, this is rotated by 55 degrees, associated with eta to be 33%. What you find is that you get a new lattice point. But the lattice point, if you look at the projection around the Q3, you will be able to differentiate between even and odd in terms of the blue and the orange. But if you look at the projection on Q4, it will have equal likelihood to be blue and orange. There's no way to tell them apart. That means if you just look at the position Q4, there's no way to infer whether it's 0 or 1 being encoded in the A1 input. So there's no information leakage from A4 mode. At least no bit information leakage. And all the bit information is transmitted through A3. There's no confusion. Similarly, we can argue for momentum, just replace Q by P. And the same argument goes through, which means there's no information leakage about the phase, whether it's plus or minus, and all the phase information also gets transmitted. Which you can get the conclusion that actually both bit and phase information, there's no leakage and all be transmitted to A3. That means all the quantum information being transmitted through A3. And actually, if you want to look at more carefully, the output, you actually get more dense lattice points, which means there are new degrees of freedom introduced. And in terms of error correction, it means that the output here is actually a quantum subsystem code. So you have one subsystem that carries over the initial input. The other system is actually entangled with this ancillary mode. So by doing this beam splitter, you actually, while generating entanglement, you also faithfully transmit information through. So that kind of shows that you can actually transmit information by carefully encoding and also put the non-Gaussian states of your ancillary. That allow you sort of kind of directing kind of like one-way mirror, information only goes the desired direction you want to go to. Okay, so now what about in practice, we only have finite energy GKP, so you need to put some Gaussian envelope of GKP, which actually, like you can here see, is kind of like a smearing for those remote lattices, and which means actually you don't need to be exactly very precise about the rotation angle because you do not have those remote lattices. So that means that when you have a large photon number, you need to be, it only works very specifically for specific etas, for specific choice of codes. But if you reduce the photon numbers, actually it works for a broader range of eta. And you can kind of, initially, you will find there are special choices of eta. It might remind you of fractional quantum Hall. But here it's actually just some like odd power divided by odd power plus some 2 times b squared. Okay, you can come up with these values, and these values can also spread out and merge with other special choice of values. So you find that actually over a wide range of eta, you will be able to come up with a good GKP code and transmit the information through. So it can be robust against loss, some finite energy GKP. And moreover, you can also introduce some of the intrinsic loss for the system that can also like sustain for these transduction scales. Okay, and I think time's up. So just a summary that we actually like look into like the Gottesman-Kittel-Presco code and come up with a near optimal recovery that allow us to fully understand like, okay, to what extent like it can correct these pure excitation loss, and also show the multimode GKP can fully achieve the quantum capacity for pure loss channels. And moreover, we can co-design quantum error correction scheme for transduction so that we can put non-Gaussian states in the ancillary that to achieve like a quantum transduction even though the conversion efficiency is less than 50%. Okay, thank you for your attention.
Could you comment on the connection to this recovery map? Like this transpose channel to the PET's recovery map? Are they the same?
Yes. Yeah, they are the same.
Oh, okay. Thank you.
Yes. Yeah.
So I was wondering, in the tri-convex optimization or the biconvex optimization, if the iteration algorithm converge, is it guaranteed that it converges to the global optimum, or maybe it is stuck at some local optimum point?
Yeah, we don't have a proof that it's global optimum. And what happened, especially for the biconvex optimization, and so even for the GKP code, there are gauge degree of freedom. Because it's pure loss channel, you can always do the rotation before the loss and then undo the rotation. It's the same. So therefore, you can always, if you have error correcting code, then rotated, in phase rotated code is also the same error. It also works effectively as well. So basically, the solution we have is, I would say, that up to that gauge degree of freedom, it seems to be like a kind of the only solution we have. But we don't have a rigorous proof. Yeah.
Thank you.
So all of your optimizations are specifically for photon loss, and maybe you can say a little bit about, like, clearly that's the dominant mechanism. Are there other things that you should worry about and how that might affect the results?
So I think that's actually like we also looked into the pure dephasing for the codes, and actually the answer is actually it's a squeezed cat code that will give you the best performance. Now, and actually for pure dephasing channel, we also know channel capacity in principle can also do similar thing. But when you have both loss and dephasing, we can show it's not this like a degradable channel. So we don't even know what the capacity is. And on the other hand, we can still numerically look for the codes. And then actually the solution is actually the convergence doesn't behave so well. It's hard to say whether it's because of the numerics we put the constraint on the photon numbers or other imperfections. But actually, like sometimes they converge to like a slightly different solutions. Yeah. So it's a little bit like ambiguous. But if you just have a dominant loss with little dephasing, it still converges to the GKP if you have finite energy state. Yeah.
Could you say maybe a little bit more about the intuition behind like the appearance of this dual lattice when you were talking about the
Yes.
you know why close packing is good? Like why is like kind of large distances in the dual lattice related to robustness?
Yes. So the dual lattice is actually corresponds to the logical operations. So let me find another example. So this is actually like again for like the square lattice GKP, and this is kind of like the basically it's a characteristic function which is related to the dual lattice. So it's basically like a Fourier transform of the Wigner function. And here you will see that actually you do have these kind of like fixed points here, which is a 2 root pi correspond to the stabilizers. And half of the stabilizer is correspond to the logical X, logical Z, logical Y. And now think about like if you have errors which will like smearing, suppose you have loss, what happens in the characteristic function for beam splitter is actually the product of the characteristic function of the input and the ancilla. If your ancilla is a vacuum, then basically just put another Gaussian envelope of the original sharp characteristic function that you have. Okay, yeah. So then you will find that these X and Z and Y will be reduced. Okay. Now in that case, you actually would want to have this like still have a good contrast of X, Z, and Y. So therefore, you actually would prefer that envelope does not significantly reduce it. But to your question, the dual lattice is actually related to these special points of the characteristic function. So you would like to have these to suffer less from the noise. Yeah.
It's somehow like the analog of like having a large distance.
Exactly. You can think like the further away means the more protected.
So I guess I'm curious, this intuition about the subsystem code, like is that generalizable to other channels as well, like multimode or even qubit channel or multi-qubit channel?
Yes. So in terms of the multi-qubit channel in here, like its bosonic system is kind of very weird because it has unbounded dimension. When you go to the beam splitter, you see these spacing kind of gets more and more dense. That actually like free up extra freedom that you can use it for either encoding or generating entanglement. Yeah, so that's how this comes. And when you say like a multi-qubit channel, we can also consider like a beam splitter with multiple bosonic modes as the input. And then the tricky thing is if I have more than 2 modes as the input, it's hard to imagine a 2-dimensional rotation, right? It's actually, if I have 3 modes, it's actually generally is a rotation in 6 dimensions. And I don't have a simple picture to understand it. So which I would say that's actually could be something interesting if one can develop a more general theory for it.
If there are no further questions, let's thank Liang again.